Welcome everyone. Today's lesson is entitled Rational Functions Day 2. This would of course be the middle lesson in our 3-day set dealing with rational functions, so it should pick up nicely from where we left off on the first day and then sets up the foundation for the culminating day, which we'll see next. And if I remember correctly, we ended with horizontal asymptotes in the day 1 lesson, which is a way to talk about the end behavior of rational functions, meaning as n gets infinitely large and infinitely small, what we found was the function values would get closer and closer to a particular value, and that value would be represented by the horizontal asymptote. So what we're going to start with is with a different type of description of n behavior. So again, as n gets large positive or large negative, what's going on with the function values of the rational functions? So as you see on your paper there, investigation 1 deals with what are called oblique asymptotes, sometimes called diagonal asymptotes. So I'm going to write a couple things in here and then we'll get rolling right away with a couple investigations. So first and foremost, oblique asymptotes are a way to describe end behavior. And again, that's exactly how we left off that last lesson. So I'll try to get all this in for you. End behavior of a rational function and it's a very specific situation. So it's a way to describe the end behavior of a rational function when the numerator, well specifically the degree of the numerator, is 1 bigger, and that's going to be the big piece, so 1 bigger than the degree of the denominator. So if you remember when we talked about the horizontal asymptotes, we compared degree of the numerator to the degree of the denominator. And there was one situation, one scenario, where there was no horizontal asymptote, and that was when the degree of the numerator was greater than the degree of the denominator. So we're going to explore that particular scenario in a little more detail here. Specifically, when the degree of the numerator is 1 bigger than the degree of the denominator, and you can see that here, degree 2 over degree 1. In this case, degree 3 over degree 2. And so if I asked you about the horizontal asymptote to these two functions that you see, you would right away tell me, oh, there's no horizontal asymptote. But what we're going to be able to do here is find maybe a better way to represent the end behavior rather than just kind of waving our hands in the air and saying, oh, no horizontal asymptote, move on. All right, and so the way we're going to do this is through just a little long division, nice little review for us. And so as it says in part A, divide the numerator of each function by the denominator and ignore the remainder. So a long story short, anytime we have a divisor that is a degree that is 1 less than the numerator as the dividend here, so divisor in the denominator, dividend in the numerator, when the degree down here is 1 smaller than the degree up there, our quotient, our answer, is always going to be a degree 1 polynomial, as we'll see. And degree 1, as we kind of know from functions, would represent what's called a linear function. And linear functions on the coordinate plane form a line. And so that is exactly how it's going to play out. All right, so anyway, without too much fanfare there, let's go ahead and get this rolling. So I've got this. So how many times does the divisor of x go into the dividend of x squared plus 2x plus 1? So starting it out, how many times does x go into x squared? It goes into x times. And as we all remember, of course, I bring this back on down, so I multiply these together and I get x squared. And then the way I do it, big subtraction symbol out in front, bring this on down here, and when this gets subtracted, that goes away. 2x minus 0 is just 2x. 1 minus 0 is just 1. So that's looking pretty good so far. And then as soon as I look at x going into 2x, That goes in positive 2 times, so it's plus 2. And here's the nice thing about this. Obviously, there's more to do. I would multiply the 2 back on down, get a remainder and all that stuff, but I don't have to do that. At the end of the day, what you're looking for, everybody, is just an mx plus b right here. And if you notice, that's exactly what I have. I have a 1x plus 2. That, long story short, is going to be the oblique asymptote for the function. Okay. Now we're going to look at this on the calculator in just a sec, but I want to make sure that you're okay with that. So I could finish up the division. I choose not to because in this particular case, all I need is the quotient being mx plus b, and I've got that right here. All right. Now before we come up and do the same thing with the function g over to the side here, I do want to look at this function f, talk about the graph itself, and see what we mean by oblique asymptote. So it's all well and good. You know, I've said, oh, this is what it is. It's a way to describe end behavior. But let's see it in action. So grab the calculators, everybody. I'm going to do the same over here. And what I'm going to go ahead and do is go to my y equals. And I'm going to go ahead and graph this function. So if you would do the same, that would be great. Just make sure I've got it all. Okay, looks good. Now I'm going to leave off the oblique asymptote for the moment. I'm just going to go ahead and hit zoom in number 6. And looking at the end behavior, do you notice as n gets larger and larger and larger, the graph is rising to infinity. And also in this case, as n gets smaller and smaller and smaller, so as the x values, as we go to the left, as x goes to large negative, we would say, notice the graph is falling, going down to negative infinity there. All right. But if you also kind of notice, if I go ahead and put my oblique asymptote in now, which is just the y equals x plus 2, you will see that the function values that I put into the y1 should be getting infinitely close to the oblique asymptote as we have it there. So you can kind of see this curve as we look at the function values. Do you see they're getting infinitely close to our oblique asymptote as n gets larger and larger and larger, and I keep saying n, but really as x gets larger and larger and larger, do you see that the function values are getting closer and closer and closer to that oblique asymptote? And from this direction, same thing. As x gets smaller and smaller and smaller, the function values are getting closer and closer and closer to that oblique asymptote. So it is a boundary line for the end behavior of the graph of a rational function. Okay, I hope that makes sense. And you can see, obviously, there's no horizontal asymptote. In this case, again, there is a diagonal or an oblique asymptote. All right, perfect. Now, let's try this other one here and see how that works for us. So x squared plus x minus 6. Again, looking that going into our dividend, x cubed minus 4x squared plus 2x and minus 5. And the nice thing about it, as said, is you don't have to go through the whole motions there. All we need is our mx plus b up here. Okay, so how many times does x squared go into x cubed? It goes in x times. I'm going to take that and distribute it into the divisor right here. So when I distribute it into the divisor, I get x cubed. I get a plus x squared. And looks like I get a minus 6x. Awesome. I put my big minus out in front. Bring that on down. Now the nice thing about the subtraction, of course, is those are going to cancel out. I do have to be a little careful with my signs here. Negative 4x squared minus 1x squared would be negative 5x squared. 2x minus negative 6x is a plus 8x, and then minus 5, of course. And then I repeat the process. How many times does x squared go into negative 5x squared? And it goes in negative 5 times. And I could multiply it back on down at this point and get my 3 terms under here. But as long as I'm confident that I got this number right here correct, then I have what I need, everybody. I have my y equals mx plus b. And so that's what I put in. So that should be the diagonal or oblique boundary line for the graph of this rational function as x gets large positive and large negative. All right, well, let's go ahead and take a look. Now, this one happens to be more of a complicated graph, and so I'm going to be a little careful. I'm going to graph it on the standard window, but I might kind of change that up a little bit depending on what we see. So if you could take a moment and graph this with me, that would be great. I'm sure you're much quicker at it than I am. Okay, and actually, I'm going to have to put parentheses there. Sorry, my bad. So let's try that one more time. Alrighty, I'll get there. And then again, you'll need parentheses for the denominator too. All right, so I think I have it in. So I graph it. And we get, let's see, we get a couple vertical asymptotes there. And we probably get that from the denominator, of course. Now, it looks like as x is getting large positive here, and again, you can just kind of see it, it looks like the graph is going up, up, up like that. We're not seeing it over here, which means just my window is not perfect for this. So I'm going to extend it out a little bit and see what we can come up with. I'm going to just try this. I don't know that this will work. But let's see if this window is any better. And again, you can change it to exactly that. That is completely arbitrary. But let's just see. Yeah, at least it's something. Yeah, it gets a little convoluted in here with that vertical asymptote. But basically, the graph looks like this. Here's one part of the hyperbola coming down that way, and then another part going up that way. And then this part down here is just not shown because of the pixels, but you can see it's sort of going like this and then up here. Now look at that M behavior. We've got this way it's going upward, this way it's going downward, but you can kind of tell like, oh, they seem to be approaching a diagonal line, and that diagonal line, of course, is defined by what we just got right here. So I plug in my y equals x minus 5, I hit graph, and look at that. So one thing to note about oblique asymptotes, like horizontal asymptotes, the graph theoretically can cross an oblique asymptote. In fact, I think it probably does in here. We would have to zoom in a little bit. But the idea is even if it crosses the oblique at some point, remember, because obliques are like horizontals. They talk about the end behavior. So what it is saying is eventually, at the end of the graph, the function values are going to get closer to that diagonal line. They're going to get infinitely close, but they're not going to touch it or cross it. Again, they can touch it or cross it in the middle of the graph, but what it's saying is eventually, as x gets larger and larger and larger, those values will get infinitely close to our line, but not touch or cross. All right, good. So now we have a more specific way to talk about a situation where there's no horizontal asymptote due to the fact that the degrees are different, greater on top than on bottom. But as you can see from a sketching standpoint, if we have an oblique, we can start looking at what our hyperbola looks like in a little more detail. All right, very nice. Let's move on to the next piece then. All right, so in the last lesson, of course, always just building on the last piece, in the last lesson we talked about vertical asymptotes, and that was where we found the function to be undefined. But there's another situation that may emerge when the function is undefined. So we might see what is called a hole. And so this investigation talks about holes versus vertical asymptotes. What's the difference? How can we tell when we'll see one and not the other? So let's go ahead. So first and foremost, both occur where the rational function is undefined. So that's what we saw yesterday. What makes a rational function undefined? Where the denominator would be 0. So let me just make sure I write this in. Both occur where the rational function is undefined. And again, if you want to make that note on your paper, it might not be a bad idea to say, you know, what will make the denominator 0. But the one thing I'll sort of say about this, both are really considered discontinuities of the function. We'll talk a lot about that as we go through this. So that's going to be our buzzword right here, discontinuities. All right, and I'll tell you what I mean by that. First things first, we've got that in play. And now what I want us to do is just, with the calculator, is to graph this and see what might be surprising from it, what might be interesting about it, and then draw some conclusions. So the first thing that I see, based on just yesterday's lesson, is I'm seeing an x minus 3 in the denominator, so that would lead me to believe that there is a vertical asymptote at an x value of 3, so a vertical boundary when x is 3. But watch what happens here, and then we'll kind of discuss why that might be. So we'll graph it, we'll sketch it, and then I'll show you what I'm looking for in this particular case. All right, so everybody go to that y equals, if you would, clear that heavy stuff out, and let's go ahead and do left parentheses 2x minus 6, and then divide by, and then again, get those parentheses going, and how about x minus 3? All right, so I'm going to recalibrate, so I'm going to hit zoom in number 6, and look what we end up getting there. We actually don't really get any type of hyperbola. What we just get is a horizontal line, and it looks like that horizontal line occurs with the y value of 2. That's kind of interesting. Okay. Now, I know you don't see it, but obviously, well, first and foremost, there's no vertical asymptote at x equals 3 when I sort of was expecting one. But what is going on when x equals 3? Because, and I'm going to go ahead and hit second trace, and I'm going to do a little value. If you notice, if I actually do try to put 3 into the function, I get 2 times 3, which is 6, 6 minus 6, so I get 0 in the numerator. I get 0 in the denominator. 0 divided by 0 is undefined. So the question is, why didn't I get a vertical asymptote? But when I do try to put in x equals 3, notice, does it give me anything? No, because the function still is undefined. I cannot do this operation up here with an x value of 3. So when x is 3, there is no function value. So even though we don't see it here, and I could zoom in, but I'm not going to do it. What I want you to do is draw it like this. We're going to draw our horizontal line, but when x is 3, everybody, it's undefined. And so what there is a little bit of a hole. And so in this case, we didn't get a vertical asymptote when x is 3, but we did get a hole, meaning I would be drawing the graph, all good, but when x is 3, I have to pick up my pencil and then draw it on the other side of 3. And so that right there is what's called a discontinuity, meaning to draw the graph of the function, I had to pick up my pencil, and I'm doing that. You might not be able to see me doing it, but I'm picking up my pencil, then drawing it on the other side. All righty? So now the question is, why did we get a hole there when x is 3 rather than a vertical asymptote? And I didn't ask you to do this, but let's go ahead and do it now. If I asked you to factor the numerator, you would take out the 2 and notice what you get. You get the same factor that produced the discontinuity. So in essence, these x minus 3's, for all intents and purposes, canceled out, and we just get the graph of the equation y equals 2, but I still can't have 3 be part of the domain of our function. So it's excluded from the domain, and it shows up as a whole. So we got the graph of y equals 2, except for the fact that there's a hole right when x is 3. Hope that makes pretty good sense. All right. Now I'm going to factor here, and let's see if you're getting the hang of this. So I'm going to factor this. It looks like it would be x plus 4 and x minus 1. So what I'm hoping you would see is that there are two discontinuities to this function. There's a discontinuity at negative 4, and there's a discontinuity when x is positive 1. So can you start to think about where I might find a vertical asymptote potentially, where I might find a hole potentially? What are we thinking here? All right, well, I'm going to go ahead and graph it. Okay, so there we go. Get this. And again, you guys are probably quicker at this, but I'll do my best. So x squared and minus 4. So we'll go ahead and sketch this graph momentarily here. Going to move that just over a little bit. All right, so it looks like we do have a vertical asymptote at x equals 1. Okay, so there is a vertical asymptote at x equals 1. There's no vertical asymptote when x is negative 4. So let's take a peek. When I try to make x be equal to negative 4, notice what happens. It cannot give me a function value because the function would be undefined for that particular x. So I don't get a vertical asymptote there, but I will get a hole there. So when x is negative 4, 1, 2, 3, negative 4, there it is. So I know we can't see it on here due to the pixels, but there's a little hole right there. All right, so if we were to draw this, it would look something like that. I think I saw something along those lines. And then here's what's kind of interesting. It would kind of go like this. And when x is negative 4, I would have to pick up my pencil and skip over when x is negative 4 and continue to draw. So a vertical asymptote at x equals 1, a hole when x equals negative 4. And I think we're starting to see the reason we got a hole here and not a vertical asymptote is because the factor that produced the discontinuity is also in the numerator. Fantastic. All right, let's do our conclusion then and continue. So holes occur when the factor that produces the discontinuity is also in the numerator. And we'll solidify this with the next example, by the way. Okay, so that's when we got a hole. Vertical asymptotes occur when the factor that produces the discontinuity is not in the numerator. And that pretty much sums it up. All right, I like it. So, with that being said, good little example just to back that idea on up. Obviously, everybody, what we need to do is when we talk about discontinuities, we are certainly focused on the bottom. But if we need to make the distinction between a hole and a vertical asymptote, we also need to factor that numerator. So what I want you to do is pause the lesson for a moment and rewrite this function in factored form. Then we'll talk about the holes versus vertical asymptotes here. All right, take a moment, do that, come on back. And if you did it correctly, the numerator nicely just is x plus 2x minus 2. That works out pretty well. And a little grouping on the denominator, just in case you forgot about that. So you get x squared minus 1, and then the x plus 2. And the x squared minus 1 should then go ahead and do x plus 1, x minus 1. And so something along those lines right there. So what that does tell me is we should have 3 discontinuities. 1 when x is -1, 1 when x is +1, and 1 when x is -2. Where would we have a hole? Where would we have a vertical asymptote? Well, let's start with the holes. This x plus 2 that produced the discontinuity is also in the numerator, and so that's where we would get a hole. These 2 factors that produce the discontinuities are not also in the numerator, and so as a result we should see vertical asymptotes there. So 1 at x equals -1 and 1 at x equals +1. All right, hope that's really clear on when we see one versus the other. Cool. All right then, let's get into just a very, very quick warm-up there, just to rehash a couple ideas, and then we'll get into some characteristics to put it all together. I like it. All right, so first and foremost, I know this is kind of silly, but it's helpful when I talk about specifically number 1 and then number 4. So that's why this is here, as you'll see momentarily. And it's funny how this gets lost in the shuffle sometimes talking to students. So 0 in the numerator, 0 divided by another non-zero constant, as we know, is 0. So when we do have 0 in the numerator, as long as that's not 0 in the denominator, we get an output or an answer of 0. Whereas if we have a divisor by 0, that's where we have it as undefined. So numerator, okay. Denominator, not so much. So this, undefined. All right, now this, the reason for doing this is to lead in to number 1 in terms of our 4 characteristics here. So vertical asymptotes and holes, as we pretty much just alluded to very specifically, really come from where the function is undefined. So I'm going to say that verbally, I'm not going to write that down, but where the function is undefined. And in a rational function, what that means is, and I put this in sort of the quotes here, they're the zeros of the denominator. Because if it makes the denominator 0, it makes the function undefined. So the zeros of the denominator, and again, now we can distinguish between a vertical asymptote and a hole based on those numbers coming from the factors and comparing it to the factors in the numerator. But essentially, where the function is undefined occurs when I would get 0 in the denominator. And that would show up as either a vertical asymptote or a hole. Okay? Horizontal asymptote. So that's just comparing degree of the numerator to the degree of the denominator. Okay? And we can even add a little piece to that puzzle. Now we have the oblique asymptote, when the degree of the numerator is 1 bigger than the degree of the denominator. So again, talking about end behavior, horizontal asymptotes, and oblique asymptotes. All right, now let's get into the y-intercept and the x-intercepts. So y-intercept is always pretty straightforward in any type of function. It doesn't change for rational functions here. So anytime I want the y-intercept, I plug 0 in for x and evaluate for y. Not too much to talk about there. That's pretty much universal. So plug 0 in for x and find out what y is equivalent to. Okay, now the x-intercepts, a little more interesting. So in order to find the x-intercepts, and this also universal, in order to find the x-intercepts, we would sort of do the opposite. Plug 0 in for y and solve for x. Now, here's where we have to be a little careful. What does that mean to plug 0 in for y and solve for x? So I'm going to take just a moment, and actually I'll go right back to this one right here. So if I wanted the x-intercepts of this function right here, let's look at this for just a moment. I would plug 0 in for y. Well, that would be this. So what I would do, and I'm going to erase this just because I don't want it to stay, but I would put 0 in for y and solve for x. Now, what did we just figure out? How do I get an answer of 0 when I'm dealing with the fraction? Well, as we just saw, and the whole reason for me to do this, how do we get an answer of 0? Well, if the numerator is 0, then the overall answer is 0. And so the way I would write this, just kind of like I did up here, if I'm looking for the x-intercepts, everybody, it would be the zeros of the numerator. Because if it's going to make the numerator 0, then it's going to make the overall function value equal to 0. All right. Well, let's wrap it up with our last example then. So determine the characteristics of the rational function here, and then sketch. So in this particular case, f of x equals 2x over x minus 1. Sounds good. Let's do this. So let's do VA slash whole. Let's do horizontal asymptote or oblique asymptote. Let's do Y-intercept and X-intercepts, because you never know, might have more. And then we'll graph. All right, now this one's a pretty basic one. You'll see that on the next lesson, they become a little more complicated, but this is a great one to end this lesson on. It really kind of rehashes everything nicely, puts everything together. All right, so first of all, discontinuities. Let's start with that. And I look to the denominator. And in this particular case, I hope you would agree we would have a discontinuity at x equals 1. The question I would have for you, of course, is it a vertical asymptote at x equals 1 or a whole at x equals 1? And based on the fact that this factor is not in the numerator, then we know it's a vertical asymptote at x equals 1. Okay, awesome. Let's talk end behavior here, horizontal asymptote or oblique. Which is it and what is it? And in this particular case, I would look at the degree of the numerator, which is 1, degree of the denominator, which is 1. And what we saw yesterday, of course, is if the degrees are the same, then we just look to the ratio of the leading coefficients, 2 on top, 1 on the bottom. So 2 over 1, and so it is a horizontal asymptote at y equals 2. Awesome. Next piece, everybody, y-intercept is I put 0 in for x. So I'm going to bring this on down here, but that would be 2 times 0 over 0 minus 1, and that equals 0 in the numerator, negative 1 in the denominator, and again, 0 divided by anything gives us 0. All right, so looks like right smack in the middle at the origin. That's where I would have my y-intercept. And then lastly, everybody, the x-intercepts. Well, how do I find the x-intercepts? I put 0 in for y. Okay, that's all well and good. How am I going to get an answer of 0 for y? It occurs when the numerator is equal to 0. So at the end of the day, all I have to do is see what would make the numerator 0. And in this case, shouldn't be a surprise because we already saw that it goes through the origin. But when the y value is 0, x is the value that produces it. All right, now let's see what we can do. So just based on this, I don't want a point plot or anything along those lines. I just want to sketch. So vertical asymptote at x equals 1. Horizontal asymptote y equals 2. Looks like just one intercept right there on the origin. Now just based on that, I should be able to figure out really what this graph looks like. So in terms of one part of the hyperbola, obviously one part of it is to the left of the vertical asymptote, one part is to the right. And with the end behavior in play, it's either going to look like this or like this. And I think you would hopefully agree with me, because it has to go through that point, it's got to be something like that right there, right? No holes or anything like that. But notice the discontinuity at the vertical asymptote because I picked up my pencil. Now I've got to draw the part of the hyperbola to the right. And the question is, to the right of my vertical asymptote, is it going to look like that, or is it going to look like that? Now, a couple ways to think about this logically. I guess the first order of business is, if it looked like this, wouldn't we have another x-intercept that it would have to cross? And there aren't any. There's just the one right here, right? So it cannot be this right here because there's no x-intercept. So what that means, of course, then has to be this. We could also talk about the multiplicities. If you remember, we talked about that on the vertical asymptote. This one's going down to negative infinity. That one's going up to positive infinity. That works based on the multiplicity of the factor that we see here. All right, as I said, we'll see some harder ones in the next. So it's like example 2, determine the characteristics of each rational function, then sketch. That's coming our way. The very beginnings of day 3, perfect continuity there, going from day 2 to day 3. All right, guys, I'll stop right there. If you have questions about anything from the lesson, do let me know, and especially as you're working on the practice problems. So thank you.